Our topic for today is real gases and its characteristics. First, what is a real gas? A real gas is a gas that does not behave as an ideal gas due to interaction between gas molecules. Any gas that exists is a real gas. Nitrogen, oxygen, carbon dioxide, carbon monoxide, helium, etc. Real gases have small attractive and repulsive forces between particles and ideal gases do not. Their behavior can be explained by interaction between the gaseous molecules. This intermolecular interaction between the gas particles is the reason why real gases do not adhere to the ideal gas law. Therefore, real gases can be defined as non-ideal gas whose molecules occupy a given amount of space and have the ability to interact with each other. 5 different examples of real gases. Almost all gases are known to be real gases since they deviate from ideal behavior under extreme conditions where the temperature and or the pressure are very high. Therefore, 5 different examples of real gases can be listed as follows. First, nitrogen. Second, oxygen. Third, hydrogen. Fourth, carbon dioxide. And the last is helium. What is the difference between ideal gases and real gases? Real gases are the gases that do not obey the ideal gas law, whereas all ideal gases must adhere to the ideal gas equation. Furthermore, an ideal gas must obey all the gas laws under all conditions, but a real gas may not obey the individual gas laws in certain conditions that are relatively extreme. It can also be noted that real gases tend to liquefy when they are cooled to temperatures that are below their boiling points. Characteristics of real gases. The actual pressure for a real gas is lower than that expected for an ideal gas. The existence of intermolecular attractive forces lowers the observed pressure in real gases. The nature of gases. Expansion. No definite shape or volume. Fluidity. Gases flow such as liquids. Low density, about 1 over 1000 that same substance as a fluid. Compressibility, can be compressed together easily. Diffusion, spontaneous mixing of the particle of two substances caused by the random motion. Effusion, the process by which gas particles pass through a tiny opening. Pressure is defined as the force per unit area. Formula of pressure, P is equals to F over A. F represents as force and A is for the unit area. Measuring pressure. Barometer, a device used to measure atmospheric pressure based on altitude. Units of pressure includes millimeter of mercury or mmHg, 1 atom or 1 atmosphere, 1 pascal, 1 newton per square meter or 1 atom is equals to 1.01325 times 10 raised to 5 pascals. Standard pressure or gas standards. 760 mm of Hg, mercury, millimeter of mercury, and 1 atom, 101.325 kilopascal. Standard temperature in Kelvin is equals to 273 Kelvin. Gas quantities. Volume, milliliter, liter, or cubic centimeter. Pressure, millimeter, kilopascals, and the temperature is always Kelvin. Here's the laws of gas. First is the Boyle's law. The pressure of a gas increases as its volume decreases, assuming constant mass and temperature. This is the formula of Boyle's law. Pressure 1 multiplied by volume 1 is equals to pressure 2 multiplied by volume 2. Pulling up increases volume and decreases pressure. Pushing down decreases volume and increases pressure. The pressure and the volume here is inversely proportional to each other. Once the pressure increases, the volume decreases. When the volume increases, the pressure decreases. Next is the Charles law. Charles law states that the volume of a gas is directly proportional to its absolute temperature, assuming the quantity of a gas and the pressure remains constant. The formula: volume 1 over temperature 1 is equals to volume 2 over temperature 2. So this means that the volume and the temperature is directly proportional. Once the volume increases, the temperature increases. Once the temperature decreases, the volume decreases also. And Gay-Lussac's law. The pressure of a gas increases as its temperature increases, assuming constant mass and volume. Pressure divided by temperature 1 is equals to pressure 2 over temperature 2. Decreasing temperature, decreasing pressure. Increasing temperature increases pressure. So it means that it is directly proportional from temperature to pressure. Once the temperature decreases, the pressure decreases. And once the temperature increases, the pressure also increases. Next is the Avogadro's law. Equal volume of gas contain the same number of molecules at the same temperature and pressure. V over N is equals to K. V1, volume 1 over N1 is equals to volume 2 over N2. Doubling the number of molecules doubles the pressure. So the N represents here the number of molecules. The pressure and temperature is constant. The combined gas law. The relationship among pressure, volume, and temperature can be mathematically represented by an equation as the combined gas law. Here's the formula of combined gas law. Pressure 1 multiplied by volume 1 divided by temperature 1 is equals to pressure 2 multiplied by volume 2 over temperature 2, where P1 is the initial pressure and the P2 is the new pressure. V1 is the initial volume and V2 is the new volume. T1 is the initial temperature and T2 is the new temperature, and temperature must always be in Kelvin. So that is the last topic of our